Good day everyone, we're your presenters for today's topic in abstract algebra, plane isometries. I'm Richen Buscato.
And I'm Rina Miumpoy. Today we'll help you understand what plane isometries are, why are they matter in geometry, and how they connect to algebraic ideas.
Alright, to start, let's remember that geometry isn't just about shapes. In abstract algebra, we study how certain transformations, movements, or operations can form structures called groups, and plane isometries are a perfect example of that connection.
What exactly is a plane isometry? A plane isometry is a transformation in the plane that preserves distance between points.
Means when a figure moves through an isometry, the shape and size never change, only the position or direction might. The distances between all points remain the same.
For example, imagine you have a triangle drawn on a paper. If you slide, flip, or rotate it, but it still matches perfectly with its original outline, that's an isometry.
Mathematically, if 2 points, for example A times the quantity of x sub 1 and y sub 1 and b times the quantity of x sub 2 and y sub 2 are a distance d apart, then after transformation, their images a prime times the quantity of x prime sub 1 and y prime sub 1 and b prime times the quantity of x prime sub 2 and y prime sub 2 are still exactly d apart.
In total, there are 4 main types of plane isometries. The first one is translation. The second one is reflection. The third one is rotation, and the last one is glide reflection. Each of these moves a shape in the plane without changing its size.
Let's think of them in simpler terms. Translation means you slide the figure. Reflection means you flip it over a line. Rotation means you turn it around a point, and a glide reflection means you slide and then flip it. So kumbaga mura siya combination sa reflection and rotation.
This transformation may look different, but they all preserve the distances between the points. That's what makes them isometries.
The first type of plane isometry is translation. In a translation, every point of the figure moves the same distance in the same direction.
For example, if a point, the quantity xy, is translated by vector ab, then its image becomes x plus ay plus b. The whole figure slides uniformly, no rotation and no flipping.
Imagine sliding your phone across a table. The phone doesn't rotate or flip, it just changes location. That's exactly how translation works in geometry.
Now let's visualize. Take triangle ABC with coordinates. The domain of A, 1, 1. The domain of B, 2 and 1. And the domain in C, 2 and 3. If we translate it by vector 3 and 2, the new coordinates are the domain of A prime 4 and 3, and the domain of B prime 5 and 3, and the last one, the domain of C 5 and 5. Same triangle, different place, but still congruent.
Second isometry is reflection. This transformation flips a figure over a line, called the line of reflection, producing a mirror image.
For example, if you reflect a point across the y-axis, the coordinates change from the quantity of x and y to the quantity of negative x and y. Across the x-axis, it becomes the x negative y-axis. The figure stays the same size, but its orientation reverses.
A good real-life analogy is looking in a mirror. Your image has the same size, but it faces the opposite direction. That's why reflection is called a flip.
In coordinate geometry, reflection helps show symmetry. For example, if a figure looks identical on both sides of the line, that line is the line of symmetry. This slide shows some example. So now let's start with translation and reflection.
For translation, think of moving a chess piece on a board straight ahead. Same orientation, same shape, the coordinates simply shift by a mixed amount.
For reflection, imagine folding a paper in half. Any figure drawn near the fold will match its mirror image perfectly. That line where the fold occurs acts as a line of the reflection.
These two examples help visualize how an object can move or flip while keeping its size and proportions. And next, let's look at rotation. This transformation turns a figure around a fixed point called the center of rotation by a specific angle.
For example, rotating the point 1 and 0 by 90 degrees counterclockwise around the origin gives 0 and 1 a 180 degrees rotation sends x and y to negative x and y. These keep distances the same but change direction.
So in everyday life, when the hands of a clock move, that's rotation. They rotate around the center, and even though they move, their shape and size don't change.
Mathematically, rotation can be represented using matrices. A 90 degrees counterclockwise rotations can be written as matrix 0 and negative 1 and 1 and 0. Now for the most complex one, glide reflection. This is a combination of a translation and reflection. Kaniha is gi-explain na ni Chen unsa to ang glide reflection.
You first slide the figure along a straight path, that's the translation, and then reflect it across a line parallel to that path. So meaning glide reflection is the combination of the translation and a reflection.
For example, imagine walking forward along the beach and seeing your reflection in wet sands. As you move, your reflection appears right beneath you. That's a glide reflection.
In coordinates, a glide reflection might look like translating a point x and y through the x plus a y, and then reflecting it over the x-axis, giving x plus a and negative y. It's two transformations combined but still an isometry since distance is preserved. So to wrap everything up, this slide summarizes all four types of plane isometries with examples.
Translation moves the figure without rotating or flipping. So mauna siyang translation. Ang reflection, flip it over a line producing a mirror image. So inig-flip ni muna siya yung mirror image, di ba? Na-discuss na ko kaganiha about ang half sa bond paper. And i-flip na mo na ay maurag hapon, dili siya magbago. Na siya reflections dari. Rotation turns it around a fixed point by an angle. I-rotate ni mo, mga manay siya rotations. So, klaro naman kay what is rotation. And the last one is glide reflection. So, ang glide reflection, it combines a translation and reflection. Or, it combines a slide and a flip.
What's special is that all these transformations preserve distance and shape. The figures remain congruent, and they only differ in how the figure's position or orientation changes.
And in abstract algebra, we can represent these isometries as functions or matrices that form a group under composition. Meaning, one transformation followed by another is still an isometry. They show the deep link between geometry and algebra.
So, when we study plane isometries, we're not just learning shapes, but we're learning how movements can follow algebraic laws.
And that concludes our presentation about plane isometries. We hope this helped you understand how this transformation works, both visually and algebraically.
Well, thank you for watching our report. We're happy to answer any questions or clarifications after this presentation. Have a great day, everyone! Bye!